Today we're going to talk about inverses of functions. Earlier in the course, we talked about relations being a pairing of elements of one set to the elements of another set. Oftentimes when we think about functions, this is the domain to the range, in which the relation pairs every input with exactly one output. So those first two bullets we'd already discussed. Now let's talk about these other ones. One-to-one functions then are where you pair every output with exactly one input. So when you plug in every x, you get exactly one y for every one of those x's, and vice versa. An inverse relation just takes that pairing and reverses it. So what was your x becomes your y, what was your y becomes your x, or if it's a inverse function, what was your domain now becomes your new range for the inverse function, and what was your range becomes your new x, or your new domain in your inverse function. So what we're going to do is we're going to test whether certain things are inverse functions or not. We're going to do this by mapping. We're going to do this by looking at points on a graph, and then we're going to be doing this algebraically as well. So let's start with mapping. Take a look at this map here. So this is my original function, let's say, and I've got these four elements in my domain. So I've got -4, 0, 1, and +4. And these are mapped such that when I plug in -4, I get back -2. When I plug in 0, I get -3. When I plug in 1, I get 2. When I plug in 4, I get 1. Okay, so this is my original function. Now for my inverse, what I'm going to do is I'm going to take each of these pairings and I'm simply going to reverse them. So here in my inverse of my function, this is now, instead of -4 to -2, I'm going to go the opposite way, -2 to -4. Instead of 0 to -3, -3 to 0. Instead of 1 to 2, 2 to 1. And then finally, instead of 4 to 1, 1 to 4. And then I've got a couple questions over here. Is the inverse a function? Okay, so to test this, we're going to look at my inverse of function mapping over here. And if each element of the domain goes to only 1 or 0 elements of the range, then it is a function. However, if I ever have anything in my new domain that goes to 2 or more things in the range, then it's not a function. So in this case, -2, one thing. -3 goes to one thing. 2 goes to one thing. 1 goes to one thing. So is this inverse a function? Yes. And is it a one-to-one function? Also yes, because one thing is going to this y, and this y is going back to just this one x if I were to reverse it. So yes. Okay, what about this mapping? This is also a function in that each element of the domain goes to one element in the range. -4 goes to just one thing, -2. 0 just goes to one thing, -3. This 1 goes to just one thing, 2, and this 4 goes to just one thing, 2. So this is a function. However, when I reverse these pairings and I look at the inverse, now I'm going from -2 to -4. We're okay there. -3 to 0. We're okay there. But then I've got this 2, which goes to 2 separate things in my new range. 2 goes to 1, and it's going to this 4. So because of this, this is not a function. A function can only be something where I plug in some value for my domain, some value for x, and I get back one answer. Here, if I plug in 2, I get 1 and I get 4. So this is not a function. And being that it's not a function, it's not a one-to-one function. So the key here, if you're looking at a map, just remember that when you're looking at whether it's the function or the inverse, each element of the domain can only go to up to one thing in the range. If you've got this going on, 2 going to both 1 and 4, this is not a function. All right, well, what about this? Here I've got these points, -1, 1, 1, 3, 0, 5, 3, 6, and I've plotted them over here. Now what I'm going to do is I'm going to take these relationships, I'm going to reverse them. I'm going to find the inverse. So instead of -1, 1, I simply swap the x and the y, just like I swapped the domain and the range above. And this is going to be 1, -1. Instead of 1, 3, this will be 3, 1. Instead of 0, 5, I've got 5, 0. Instead of 3, 6, this will be 6, 3. All right, what happens if I were to take these new points and plot them on here? Let's find out. 1, -1, so over 1, down 1. Got this point right here. 3, 1, so 3, then up 1. 5, 0, go over to the right 5. And finally 6, 3, so over 6 and 1, 2, up 3. So these are my new points. These are the inverse points here. And what do I notice about the graph after plotting the new points? Well, it kind of looks like I've got some symmetry, right? So if I do this, I can see that I've got some symmetry happening. So how am I going to answer this? I'll say that there is symmetry now in the graph. And what are these points' relationship? What's the relationship to the line y equals x? Well, this line right here is y equals x, and y equals x is our line of symmetry. So what I see up and to the left is what I'm going to see down and to the right. What I see up to the left is what I'm going to see down and to the right. Okay? Same thing here, and over here, here, and over here. So what is the relationship? Y equals x is the line of symmetry. Now, I want to remember this y equals x later on in the lesson. But first, let's talk about finding the inverse of a function. I've got a few steps. To find the inverse of a function, I'm going to do these 3 things. 1, I'm going to replace f of x with y. F of x is function notation. It's just kind of fancy for y. So I'm going to replace it, a little too fancy for me, make it y. Then I'm going to solve for x, step 2. This is going to be a little bit longer than the other steps here. And then step 3, once x is solved, I'm going to swap x and y. So this is actually then taking the inverse there. And then to show this back in function notation, I'm going to replace the y with this f to the -1 of x. This means f inverse of x. Or in other words, the inverse function of whatever my original f function was. So let's say my original function is this. F of x equals 3x plus 4. Let's follow those 3 steps. I'm going to first replace f of x with y. Y equals 3x plus 4. Then I'm going to solve for x. Okay, so I've got 3 times x plus 4. Let's start to undo some of these things. I'll subtract 4 from both sides. Now you could write y minus 4 on the left side here equals 3x on the right side. Because I know step 2, I'm solving for x, I'm going to put 3x on the left is equal to y minus 4. I just think that looks a little bit nicer. Then let's divide both sides by this 3. All right, what am I left with? X equals y minus 4 over 3. I've solved for x. I've got x by itself. And now, once x is solved, I'm going to swap x and y. So anytime I see an x here, this is going to become a y. And anytime I see a y, this is going to become an x. So I've got y equals x minus 4 over 3. And if I change this back to function notation, this is the same as saying f inverse of x equals x minus 4 over 3. This is my inverse function. Okay, so let's talk graphically then. What's happening here? As you see, this dashed line is my y equals x, and then one of these lines is my original and the other is my inverse. And take a look. Just like when they were just a few points, now technically these are lines, so this is infinite points, we're still symmetrical about this y equals x. Let's do this one more problem like this. Let's do f of x equals 2x minus 2. I'm going to follow those same 3 steps. So step 1, f of x, a little fancy. Let's just change this to y. Y equals 2x minus 2. And then step 2, let's solve for x. So I'm going to start to undo everything. I'm going to add 2 to both sides. Here I'll get 2x equals y plus 2. Divide both sides by this 2 here. And this will give me x equals, now I'm going to write this as y over 2 plus 1. Just to change things up, show you that there's a number of different ways that you could write this, but they all mean the same thing. So in this case, instead of writing y plus 2 over 2, I'm just going to divide each of those by that 2, leave the first one as y over 2, and then 2 over 2, 2 divided by 2 becomes 1. Okay, then step 3. I'm going to swap the x and the y. So now this becomes y. This y over here becomes x. And I'll get y equals x over 2 plus 1. And then let's change this back to function notation. F inverse of x, to show that this is the inverse of my original function f, is equal to x over 2 plus 1. Okay, and same as the other one, here I've got that y equals x again, that dashed green line right here, and I'm showing that both the function and its inverse are symmetrical about that line of symmetry, y equals x. One more thing to talk about. Function composition. You may recall this from earlier classes as fog, so f of g or g of f. This is where you take one function and essentially you are plugging it into the other function. You're evaluating a function where instead of saying, find f of 2, where you plug in 2 for every x, or f of 5, where you plug in 5 for every x, you are going to plug in an entire function in for x. So you're still going to be left with an x of some sort at the end. Okay, let's use function composition with inverse functions. So in example A, we were given a function f of x equals 3x plus 4, and we found the inverse of this function to be f inverse of x equals x minus 4 over 3. What is f inverse of f of x? Or in other words, if I take my inverse function and I use that as a base, and I plug in my original function and I evaluate that, what do I get? So let's see. F inverse of x. This is x minus 4 over 3. And what I'm going to do is I'm going to take this f of x equals 3x plus 4, and I'm going to plug in f of x for x, which really means taking 3x plus 4 and plugging that in for this x here. So what will that look like? That's going to be f inverse of f of x, plugging in f of x into f inverse, equals, instead of this x minus 4, this is going to become 3x plus 4. And then I'm still going to have everything else. So I'm still going to have minus 4 at the end over this 3. So all I've done is replaced this x here with the other function, 3x plus 4. Just to get 3x plus 4, and then minus 4 still, over 3 still. Okay, well, 4 and negative 4, 4 minus 4, that's going to go to 0. Let's subtract those out. This leaves 3x over 3. And of course, 3 divided by 3 is 1, so these are going to divide out. And you're left with just x. Interesting. And that's because if you use function composition with two functions that are inverses, you will always get back just x. Let me say that one more time. If you use function composition where the functions are inverses of each other, you will always get back just x. And the thing is, you could do that whether you take your inverse function and use that as your base and you plug in your original function into it like we did here. And you'll also get x if you just use your original function and then you plug in your inverse function into your original function. Both will work. So when I look at this one, in example B, we had f of x equals 2x minus 2, and the inverse that we found was f inverse of x equals x plus 2 over 2. What I'm going to do is I'm going to show you, okay, this is going to be using the original function as a base. And then over here, let's do this. Let's say that this is using the inverse function as a base. What that means is on the left side, I'm going to start with f of x equals 2x minus 2. And then I'm going to say f of f inverse of x, meaning I'm going to plug in my inverse function into my original function. So every time I see an x, instead of 2x, this will be 2 times, and then I plug in x plus 2 over 2. And I still have minus 2 at the end. Whereas over here, I'm going to start with f inverse of x. So this is my inverse function. This is x plus 2 over 2. And what I'm going to do is I'm going to take this and I'm going to plug in my original function. So instead of x plus 2 over 2, I will get 2x minus 2, and then still plus 2 all over this 2. On the left side, let's see, this 2 will multiply into this fraction. We're going to multiply it to the numerator, but then we end up dividing by this 2, so these will end up dividing out. You'll get x plus 2 minus 2, which of course, 2 minus 2, that's going to go to 0. That's going to subtract out, leaving just x. Okay, over here, let's look at the top part first. We've got minus 2 and then plus 2. That's going to subtract out. This will leave 2x over 2. then 2 over 2, these will divide out to 1, leaving again just x. So it doesn't matter which way you do this, as long as they are inverses of each other. When you use function composition, you will get back just x. So you may have some problems where you're given two functions and you're asked to show that they're inverses, to show that they're inverses. So what that means is just use function composition, plug one into the other, doesn't matter which way you do it. And if you get back x, those are inverses of each other. If you get back anything else, then they are not inverses of each other.